Noche cósmica.
There exists, at this very moment, a world of ice and stone so distant from the sun that it takes 248 years to complete a single orbit. 248 years. During that same span, multiple human generations are born, live their lives, and pass into history. Yet this small, strange world, Pluto, as many still call it, is merely one of thousands of such bodies drifting in the cold reaches beyond Neptune, and perhaps one of the gentler ones to contemplate as you drift towards sleep yourself. The dwarf planets are among the least disturbing celestial objects to consider in the deep hours of night. They do not threaten us. They do not command the gravitational authority of the great gas giants or the fierce attention of the rocky inner worlds. Instead, they exist in a realm of profound quietude, where the sun's warmth has diminished to merely a bright point of distant light, where the concept of day and night becomes nearly meaningless, and where time itself seems to move differently. They are frozen archives of the solar system's earliest hours, locked in their slow dances around a star that, from their perspective, is scarcely brighter than Venus appears to us on a clear winter evening. If you have ever wondered what it might feel like to leave everything familiar behind, the noise, the urgency, the constant pull of gravity that keeps you bound to Earth, then perhaps you would find solace in imagining the experience of these distant worlds. They exist in a kind of permanent twilight, orbiting through regions where the vacuum is so complete, so perfectly empty, that sound itself has no medium through which to travel. There is only cold, only the faint radiation of distant stars, only the slow, patient geometry of orbital mechanics playing out across centuries and millennia. We are going to travel outward together, moving from what you know toward what remains mysterious. Not in any hurried sense, but with the patient deliberation of a spacecraft itself, carrying data and instruments across years of interplanetary space. And if you find yourself drawn to these stories of distant, quiet worlds, to the peculiar peace that comes from contemplating places where nothing changes rapidly, where processes unfold across timescales that dwarf human lifespans, you might consider subscribing to explore more of these relaxing facts about dwarf planets, the forgotten kingdoms of our solar system, where we can glimpse the universe's most ancient and tranquil secrets. The journey outward begins not with dramatic discovery, but with a kind of persistent curiosity. For much of human history, we imagined the outer solar system to be a place of completion and finality. The Sun, Mercury, Venus, Earth, Mars. Then the asteroids, those fragments scattered between the orbits of Mars and Jupiter. Then Jupiter itself, Saturn, and eventually, as telescopes grew more powerful and ambitious, the distant giants Uranus and Neptune. The solar system seemed to have an edge, a boundary beyond which there was nothing particular, just the vast, unstructured void of interstellar space. But something was amiss with this neat conception. Mathematicians noticed small irregularities in Neptune's orbit, tiny deviations that suggested an unseen body was exerting gravitational influence from farther out. The calculations were subtle, almost imperceptible to the instruments of the 19th century, yet they persisted. There was something out there, something cold, something waiting. Imagine standing in an observatory in the 1840s, before this discovery, looking up through a telescope at a sky full of points of light, most of them barely resolved into anything more than suggestions of brightness. The night sky offered few certainties beyond what had been known for millennia. Now imagine the moment when certainty shifts, when the invisible becomes visible, when a body that has been orbiting the sun for billions of years finally registers itself upon human consciousness through the careful application of mathematics and observation. This is how the outer solar system began to reveal itself to us, not as a sudden flash, but as a slow, patient accumulation of knowledge. The telescope grew more refined. photography emerged, allowing astronomers to capture the positions of celestial objects with unprecedented precision. Photographic plates were compared, one exposure overlaid against another, taken months or years later, searching for any point of light that had moved against the background of fixed stars. This was patient work, detective work, the kind of systematic observation that requires both meticulous attention and a willingness to spend long hours examining images in dim light, searching for the barely perceptible. And in this quiet, methodical fashion, the dwarf planets began to emerge from obscurity. Not all at once, but gradually, over more than a century and a half of careful observation, each one a surprise, each one a small mystery partially solved, only to give rise to larger questions about how the solar system formed, how its bodies became distributed across such vast distances, and what stories their surfaces might tell those patient enough to listen. As we move outward now, visualize the space you are traveling through. The light from the sun diminishes with each million kilometers. The temperature drops precipitously, not in any dramatic collapse, but in a steady, inexorable decline. At the orbit of Earth, the sun's energy still warms the surface and drives the weather systems that sustain life. But as you move beyond Mars, beyond the asteroid belt, the heat becomes increasingly theoretical. By the time you reach the realm of the dwarf planets, the sun's warmth is nearly absent. What light reaches these worlds is pale and cold, casting long, dark shadows across cratered landscapes of ice and ancient rock. The silence out there is absolute. There is no atmosphere to carry sound, no wind, no rushing water or rustling leaves. Only the slow, silent pull of gravity, keeping each world in its orbital path, and the patient passage of time, measured in orbital periods rather than years. A dwarf planet might orbit the sun fewer times than it takes a human to grow old and pass away. Some orbit so rarely that the civilizations that discovered them will rise and fall many times before these distant worlds complete even a single lap around their star. This is the realm we are entering now, together, in this moment. The outer solar system, the land of perpetual cold and eternal silence, the home of the dwarf planets, where the rules of physics still apply, but where time itself seems to have adopted a different rhythm. And it is in this spirit of contemplation and patience that we begin to encounter them, one by one, each with its own peculiar story, each a repository of ancient mysteries, each as it drifts in the profound dark, waiting quietly for the universe to unfold around it. And as we drift further outward, through the thinning light and the patient cold, you might find yourself wondering what else is waiting out there, turning slowly in the dark, asking few questions of the universe, and receiving even fewer answers. The dwarf planets, those small, distant worlds that have only recently earned their own gentle category in our cosmic taxonomy, hold something profoundly quieting about them. They are not the attention seekers that planets are. They do not dominate their orbits or gather the brightness of the sun in quite the same commanding way. And yet they have stories, subtle, layered stories that take time to unfold, that reward patience, that ask us to sit still and listen. If you find yourself drawn to these quieter corners of the solar system, to the slow revelations that come when you learn about worlds that most of us will never speak of in ordinary conversation, there is a place here where we gather to explore them together, where we journey outward at the pace of thought itself, where distance becomes a kind of meditation, and where the history of distant ice and ancient cratering marks itself out not as drama, but as gentle facts, unfolding like frost, spreading across a window in the deep of winter. We explore the dwarf planets not as anomalies or failures, but as the true architects of the outer solar system, the worlds that shaped what came before us, and what will come long after our small sun has dimmed. Each mission into the void brings new details, new layers of understanding about these distant spheres, and those details deserve to be held carefully, spoken of with the reverence they warrant. So as we continue now through this slow passage into the outer reaches, knowing more deeply who these small worlds are and what they have endured across billions of years, consider subscribing to these journeys. Let yourself return to this quiet place, where we move through space at the speed of whispered inquiry, where every fact is an invitation to rest a little deeper, and where the universe itself becomes less a place of overwhelming vastness and more a gentle landscape you can settle into, fold into, lose yourself within. The dwarf planets will be waiting, turning their slow rotations, reflecting the distant sun across their frozen surfaces, ready to share what the years have taught them. And we will be here, speaking about them in the dark, in the stillness, drawing closer to them and to sleep itself with each discovery we share. In the late 1700s, long before anyone had even heard the word dwarf planet, astronomers were noticing something peculiar in the mathematics of the solar system. The planets they could see, Mercury, Venus, Earth, Mars, Jupiter, Saturn, and later Uranus, they all obeyed Newton's laws with remarkable precision. Their orbits could be calculated, predicted, verified. But there was a curious gap, a whisper of wrongness in the data. When they looked at where Uranus should be, based on the gravitational pull of all the known planets, it was always just slightly out of step, almost imperceptibly off. Like listening to a distant orchestra and hearing one instrument playing a fraction too early or too late. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, began what might be called the most patient form of detective work. Instead of looking through telescopes at the night sky directly, they worked in rooms lined with numbers and calculations, following the traces of an invisible hand. They reasoned backward from the perturbations in Uranus's orbit, working out where an unseen gravitational presence would have to be to explain what they observed. It was a kind of celestial archaeology, searching for a world by its effects rather than its light. And then, in 1846, an astronomer named Johann Galler in Berlin pointed his telescope to the spot where the mathematics said something should be, and there it was. Neptune, a pale blue world that no human eye had ever seen before, revealed first as an idea, then confirmed as reality. It was as if the universe had been waiting for humanity to learn to think in this particular way. This discovery planted a seed. If there was an undiscovered planet hiding beyond Uranus, might there be another one still further out? The question began to settle into the minds of observers. For decades after Neptune's discovery, astronomers looked and calculated and wondered. The evidence was subtle. There were tiny irregularities in the orbits of both Neptune and Uranus that seemed to suggest one more massive world might be out there, somewhere in the vast darkness beyond. Not all astronomers were convinced, but the possibility existed, and once a possibility exists in the scientific imagination, it doesn't leave easily. By the late 1800s and into the early 1900s, sky surveys began in earnest. Observatories around the world, from the Lowell Observatory in Arizona to institutions across Europe, started systematic photographic surveys of the outer solar system. Photography itself was relatively new, and it changed everything. Instead of relying on what a human eye could see in a single night, astronomers could now record the sky on long exposures, accumulating light over hours, revealing objects too faint for the naked eye to detect. They could also compare plates taken on different nights. If a star had moved between two photographs, it might not actually be a star at all. It might be something much closer, something orbiting. The work was slow and methodical. Clerks and assistants would spend hours comparing photographic plates side by side, looking for that telltale shift. Imagine staring at two nearly identical images, searching for the one speck that had moved. It required patience, focus, and a kind of meditative attention. There was no urgency to it. There was only the quiet confidence that if something was out there, it would eventually reveal itself to careful enough looking. The Lowell Observatory in particular became associated with this search. Percival Lowell himself had passed away in 1916, but his dream of finding a ninth planet persisted in the minds of his colleagues. The observatory continued the work, taking plate after plate, comparing, calculating, refining the predicted location where this hypothetical world should be. Decades passed. The search became something almost ceremonial. How long can you look for something you're not even certain exists? What strikes us now, from a distance, is how gentile this process was. There were no algorithms, no computers to rapidly sort through thousands of images. There was no way to rush it. You simply looked and looked again, and trusted that persistent attention would yield results. The detective work of early astronomy had a rhythm to it, a patience that feels almost restful when we consider it from our current age of instant digital searches. These astronomers were engaged in the very long game, and they seemed content with that timeline. And so the stage was set. The idea of another world was out there, floating in the collective mind of the astronomical community. Somewhere in the frozen darkness beyond Neptune, something was waiting to be discovered. The tools existed now. The search parameters had been calculated. All that remained was the slow, careful work of looking, comparing, and waiting. The dwarf planets themselves didn't yet have a name or a category. They were simply the possibility of worlds, and that possibility had become too real to ignore. In the beginning of the 19th century, when telescopes were still simple affairs, and the night sky held far more mystery than it does now, astronomers noticed something curious in the region between Mars and Jupiter. There was a gap, not a literal emptiness, but a mathematical one. The orbital spacing of the known planets seemed to suggest something should exist there, a world waiting to be found. And so, in the early hours of January 1st, 1801, on that threshold moment between centuries, an Italian astronomer named Giuseppe Piazzi was sweeping his telescope across the Taurus constellation when he spotted a faint point of light that shouldn't have been there. He watched it move against the background stars. Night after night, it was in a different place. He had discovered Ceres. The name itself carries ancient dignity, the Roman goddess of agriculture, of grain and harvest, fitting for a world that would eventually teach us about the origins of water and life itself. But at first, nobody quite knew what Ceres was. Piazzi called it a comet. Within months, other astronomers observed it and began to wonder if perhaps it was something else entirely, something larger and more orderly in its path. It possessed the calm, predictable orbit of a planet, but it was vastly smaller than any of the 8 known worlds. The astronomical community entered a period of quiet disagreement, a waiting time. Was this a new planet, a large asteroid? There were no clear categories yet. For more than a century and a half, Ceres remained in a kind of limbo, catalogued and observed but undefined. It orbited patiently in the asteroid belt, a region so sparse that the popular imagination would long misrepresent it, not as the silent, cavernous emptiness it truly is, but as a dangerous field of tumbling rocks. The reality is far gentler. Objects in the asteroid belt are separated by vast distances, each one isolated in its own pocket of silence. And there, among them, Ceres continued its ancient revolutions, unmeasured and mostly forgotten by the wider world. What we could not see from Earth, what required spacecraft to finally perceive clearly, was the remarkable nature of Ceres' surface. It is not a simple grey rock. Its face is pocked with impact craters, like so many worlds, but beneath that scarred exterior lies something of profound importance: water. Vast quantities of water, locked away in the form of ice, residing just beneath the regolith and stone. Ceres is, in many ways, a frozen reservoir. If you could collect all the water in Earth's oceans and place it on the scale of a solar system, Ceres would contain nearly a third of all that water, all suspended in a state of crystalline stillness, preserved for billions of years. This ice is not randomly distributed. Through spectroscopic analysis, through careful study of how light reflects from different regions of Ceres, astronomers have mapped where the water-rich materials cluster most densely. In the shadowed craters near the poles, where sunlight barely penetrates and temperatures remain perpetually frozen, the concentrations grow richest. These are cold traps, places where volatiles can accumulate and persist in a kind of geological stasis. When you gaze upon Ceres' surface through the lens of these findings, you begin to see not a barren, dead world, but something far more alive with chemical potential, a planetary archive of ices that have endured since the formation of the solar system itself. The surface topography tells a deeper story still. There are mountains on Ceres, some of them quite tall relative to the world's small size, and among them flow what appear to be ancient flows, channels perhaps carved by material that was once more fluid than ice ordinarily becomes. Some of these features have prompted careful speculation among scientists. Might there have been, in Ceres' distant past, regions warm enough for briny water to exist, not beneath the surface alone, but in liquid movement across it? The evidence is subtle, and the scientific community remains appropriately cautious, yet the possibility lingers. There is something profoundly moving about the idea of ancient, slow rivers of salt water trickling across a world so cold and remote that we could barely see it until very recently. Within Ceres' cratered landscape, there are places where material rises in low domes, gentle swells in the terrain that might represent cryovolcanism, the eruption of ice and brine mixture instead of molten rock. Such events, if they have occurred, would have represented moments of relative warmth and activity in what we otherwise understand as a frozen, stable world. They speak to internal heat, to geological processes that persist in the deep places where we cannot reach. And yet the overwhelming impression that emerges from all of this data is one of stillness, of preservation. Ceres holds secrets from the early solar system, locked in ice, waiting for the patient gaze of instruments that can read its surface from millions of miles away. The reclassification of Ceres came much later, long after these discoveries of water and ice. For decades, as telescopes improved and more asteroids were found in the belt, Ceres was simply listed as the largest asteroid, a special case, almost an honorary position. But the definitions of planetary science are not static. They evolve as our understanding deepens. And in the early 21st century, as astronomers detected more distant objects of similar size orbiting beyond Neptune, the question arose once more: what is Ceres, really? The answer arrived gently, without drama. Ceres was reclassified as a dwarf planet, a category that acknowledges both its planetary characteristics, sufficient mass to achieve a nearly round shape under its own gravity, and its differences from the classical 8 planets. It is a world, but a small one, a body of geological significance, but distinct in origin and composition from those rocky terrestrial spheres or distant gas giants. There is something oddly peaceful about this classification, despite the public controversy that surrounded Pluto's similar reclassification around the same time. For Ceres, moving from asteroid to dwarf planet is a recognition rather than a demotion. It confirms what the ice and the craters and the gentle topography have always suggested, that this is not merely rubble, not merely the collision debris of a violent era, but a world unto itself, a keeper of water, a monument to the solar system's ancient past, frozen and waiting, orbiting still in that vast and silent region between the close warmth of Mars and the distant reaches beyond. When the Dawn spacecraft finally arrived at Ceres in 2015, after a journey of more than 8 years, its cameras began to reveal something that would transform our understanding of this small world, something that had waited in the silence of the asteroid belt for billions of years. There, in a crater called Ocata, lay something that should not have been there, or perhaps something that had always been there and was only now being seen. Bright, luminous patches of material gleamed across the crater floor, catching the sunlight in ways that seemed almost to defy explanation. These were not mere rocks or dust reflecting light differently. They were something far more intricate, far more curious: sodium carbonate, salt. The discovery arrived like a gentle whisper of mystery. Scientists had long suspected that Ceres harbored vast reserves of water ice beneath its surface, a dwarf planet so rich in frozen water that some researchers had begun to wonder if it might be less a world of rock and more a vast ancient ocean, now dormant and deeply buried. But these bright spots suggested something more haunting still. They hinted at something that had once flowed, something that had moved across the surface in a form now long cooled and crystallized. The sodium carbonate deposits, scientists reasoned, could only have arrived at the surface through one mechanism. They had been carried upward by briny solutions, saltwater brine rising from deep within the dwarf planet's interior, seeping slowly upward through cracks in the crust until it reached the cold vacuum above, where the water would evaporate and freeze, leaving behind these white mineral traces. Picture, if you will, a vast underground reservoir of salt water somewhere deep beneath Ceres' grey exterior. Imagine the pressure of a moon's weight pressing down upon it. Imagine the faint warmth from radioactive decay deep in the interior, perhaps even the friction of tidal forces from the sun pulling gently at the world. Over immense spans of time, millions of years perhaps, this brine would find its way through fractures, through ancient fissures in the crust, ascending like a very patient tide toward the surface. And there, in the crater called Ocata, it would emerge into a sunlit bowl of rock, and in emerging, it would transform. The water would escape into the thin vacuum, carrying away into the empty darkness, but the salts would remain, white and bright and mysterious. The implications unfold slowly, like the opening of a flower that blooms only once every million years. If Ceres possessed liquid water in its remote past, and perhaps even now, in its deepest places, then the dwarf planet becomes something more than a cold, inert stone. It becomes a place where chemical processes could occur, where the building blocks of what we might generously call prebiotic chemistry could gather and interact. The thought is not that life necessarily emerged there. It is far too early in our exploration to make such claims. Rather, it is that Ceres might have possessed, at some point in its history, the fundamental conditions that life requires: liquid water, chemical complexity, and time. So very much time. The Ocata crater itself, scientists have determined, is relatively young, perhaps less than 200 million years old, a mere adolescent in cosmic terms. And yet, even in its youth, it seems to carry signatures of something older, something that speaks to the interior world. Other smaller bright spots dot Ceres' surface in other locations, less dramatic than Ocata perhaps, but equally tantalizing in what they suggest about the hidden reservoirs beneath. They cluster in certain regions, they follow certain patterns, and in following these patterns, researchers have begun to map the invisible geography of the moon's interior, tracing pathways where ancient brines might still be finding their way upward, molecule by patient molecule. What lies in the depths of Ceres now is a question that remains largely unanswered. Is there still liquid water down there, preserved in pockets of rock and ice, insulated from the terrible cold above by layers of frozen material? Or has the entire moon frozen solid over its billions of years, the once liquid reservoirs now transformed into permanent ice. The evidence is ambiguous, inviting speculation but resisting certainty. Some researchers have proposed that Ceres may actually be more water than rock, that it might be better understood as an ocean world, frozen and dormant, waiting in the dark. Others suggest a more complex picture, a geology of layered ice and rock, with liquid brine persisting in only the warmest regions, perhaps near the core. The Ocata bright spots remain one of the most tranquil mysteries of the outer solar system. They speak of a world in slow transformation, of ice and salt and water in conversation across billions of years. They remind us that even in places that seem lifeless and cold, there is activity, there is chemistry, there is the patient work of time reshaping matter. And somewhere in those white deposits, in the crystallized remnants of ancient brines, there may be traces of a younger Ceres, a world perhaps more animated than it is now, a moon where chemistry was more vigorous, where the boundaries between inorganic and organic were beginning to blur. The silence around this little world is profound. It orbits in the asteroid belt, surrounded by millions of smaller bodies, yet few of them shine as brightly as those patches in Ocata. It is as though Ceres is calling out in a language made of salt and light, telling a story that humanity has only just begun to learn how to read. The search for Pluto began not with telescopes pointed at the sky, but with photographs. In the early decades of the 20th century, astronomers had noticed peculiarities in the orbits of Neptune and Uranus, small irregularities, subtle wobbles that suggested an unseen gravitational hand was gently tugging at these distant ice giants from somewhere beyond. The mathematics of those orbital disturbances pointed to a world that ought to exist, a ninth planet waiting to be found. But finding it would require patience of a kind that modern astronomy rarely demands anymore. Enter Clyde Tombaugh, a young man from Kansas, whose family had moved to Arizona, and whose passion for the cosmos had led him to the Lowell Observatory in Flagstaff. He was not a formally trained astronomer in the traditional sense. He was a careful observer, with steady hands and an extraordinary capacity for patient, methodical work. In 1929, at just 24 years old, he was given an assignment that would define his life: photograph the same region of the night sky, again and again, and compare the images plate by plate, looking for anything that had moved. It was tedious, deliberate work, the kind of astronomy that asks not for brilliance in a single moment, but for an almost meditative consistency across months and years. Night after night, Tombaugh would make his photographs. The telescope would gather light from distant stars and planets, focusing it onto glass plates coated with emulsion. He would develop these plates in darkness, then mount them on a device called a blink comparator, an instrument that allowed him to look at two photographs alternately, switching between them in rapid succession. As the images flickered back and forth before his eyes, any object that had moved between one exposure and the next would appear to jump, to dance slightly, standing out against the fixed backdrop of eternal stars. For months, nothing remarkable emerged. The work was monotonous, in a way that might have worn down a different temperament, but Tombaugh seemed to find something meditative in it. He developed an almost intuitive sense for the patterns of starlight, learning to read the plates as one might learn to read a familiar text. And then, on February 18th, 1930, something moved, a faint point of light, barely distinguishable from the stars around it, had shifted position between two plates taken 13 days apart. Tombaugh recognized it immediately. After 75 years of searching, the ninth planet had been found. The world was named Pluto, a fitting choice given its status as the farthest, coldest, and darkest of the known planets. The name drew from the Roman god of the underworld, and there was poetry in that. A world so distant that sunlight reached it only as a pale whisper, so remote that it dwelled in a kind of cosmic darkness. The discovery made Tombor famous, and in the decades that followed, Pluto occupied a peculiar place in human imagination. It was the ninth planet, the outermost guardian of our solar system, and its very discovery represented the triumph of patient, methodical observation. For 76 years, Pluto would hold that title. Children grew up learning of 9 planets in their schools. The names became rote, familiar: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Generations of people learned to count the solar system this way, to imagine these 9 worlds in their orderly procession around the sun. There was something satisfying about that number, that clean decimal just short of 10. Pluto became iconic in a way that perhaps no other dwarf planet ever could. Not because it was the largest or most unusual, but simply because it was ours, the world we had discovered, the furthest beacon of planetary order. And yet, even as Pluto held this honored place in public consciousness, astronomers had begun to wonder. As telescopes improved and technology advanced, observations began to accumulate. Pluto, it seemed, was smaller than expected, smaller, in fact, than Earth's moon. Its orbit was unusual, tilted at an angle to the plane of the other planets, and oddly elliptical in shape. There was something about Pluto that didn't quite fit the profile of a true planet, something that spoke to a different origin story. But these were quiet concerns, shared in the community of professional astronomers. To the wider world, to the public imagination, Pluto remained simply and unquestionably the 9th planet. What would it have been like, one might wonder, to think of the solar system in that way, as a complete, ordered set, with Pluto as the final, absolute boundary? There was something reassuring about it, perhaps. A sense of closure, of a world fully mapped and understood. The idea that we could point outward and say, there, that is the edge, that is as far as the planets go, and beyond that, only the vast, uncharted darkness of space itself. For more than 70 years, Pluto lived in a kind of settled certainty. It had a place, it had a name, it had a number, the 9th. And then, in the early 21st century, astronomers began to find other objects in the outer reaches of the solar system that looked, in many ways, quite similar to Pluto, not identical, but remarkably alike. And this quiet discovery opened a question that would gently unravel everything people thought they knew about the order of things. The International Astronomical Union, that careful guardian of celestial names and categories, found itself facing something that might seem simple on the surface, but which revealed itself, upon reflection, to be quite profound. What exactly was a planet? Not what is Pluto, but what are the characteristics that define a planet at all? The question had never been formally answered. In the age of telescopes, when planets were few and distant, and clearly distinct from stars, there had been no need to write the definition down. Everyone knew, everyone could agree, but knowledge, it turns out, is only stable when it remains untested. The debate that unfolded in 2006 was not, as it has sometimes been portrayed, a moment of controversy and loss. Rather, it was something quieter and more philosophical. It was a conversation about language itself. How do we organize the universe in our minds? How do we decide what belongs in which category? And once we have decided, what do we do when the universe reveals that its boundaries do not align with the boxes we have drawn? Astronomers examined the criteria. A planet, they began to propose, should orbit the sun. This much was clear, but there was something else. A true planet, in the vision that emerged from this careful deliberation, should have enough mass to pull itself into a roughly round shape. This is a profound threshold, actually. It represents a shift in the object's power. Once something becomes massive enough, gravity wins. The object becomes a sphere. It becomes, in a sense, resolved. And then there was a third criterion, and this was the one that would change everything for Pluto. A planet should have cleared its orbital neighborhood. It should gravitationally dominate the region around it, pulling in or scattering away the smaller bodies that share its path. This is how our 8 larger planets behave. They have swept their neighborhoods clean. They have imposed order. Pluto, when examined against this standard, met the first 2 criteria comfortably. It orbited the Sun. It had sufficient mass to assume a roughly spherical shape. But the third criterion, the neighborhood clearing, Pluto had not done. It had never done this. Its orbital path was crowded with other small icy bodies. Pluto was, in many ways, the largest of these objects. But it shared the space. It had not dominated. It had not cleared. And so, on August 24, 2006, the International Astronomical Union issued its decision. It was not a demotion, precisely. It was a reclassification. It was a recognition that Pluto occupied a different category from the 8 planets. But what would that category be called? The term they settled upon was dwarf planet. And alongside Pluto in this new classification, they placed Ceres, the quiet body that had orbited in the asteroid belt for so many centuries. Ceres too was massive enough to be spherical. Ceres too had not cleared its neighborhood, and there would be others to follow. Makemake, Haumea, Eris. Eventually, dozens more would join this growing family of small, icy, spherical worlds that orbited the Sun, but did not govern the spaces around them. The beauty of this decision, if we pause to consider it without the weight of sentiment, is that it was fundamentally honest. It was taxonomy born not from rejection, but from observation. The universe had revealed its own structures. Pluto had always been what it was. It had not changed. Our understanding had simply caught up. The definition had been made clear. And in clarifying the definition, we had given ourselves a lens through which to understand so much more. We had opened a door to a whole category of worlds that had been waiting, patiently, in the cold dark, to be properly named. What remains, then, is not a loss but an expansion, an enrichment. The solar system had not fewer categories now, but more. The story of Pluto's reclassification is the story of language catching up to reality. It is the story of how we organize our understanding of the cosmos, moment by moment, as new knowledge reveals itself. And in the process, we had finally turned our attention to these smaller worlds, these dwarf planets, and begun to ask what secrets they might hold. When New Horizons finally approached Pluto, after a 9-year journey through the deep cold, the spacecraft's instruments began transmitting back images that would reshape everything we thought we understood about this distant, tiny world. What emerged on the screens of eager astronomers was not the cratered, airless sphere that many had expected, but something far more alive with quiet geology and unexpected features. The most striking of these lay immediately visible on Pluto's sunlit face, a vast, heart-shaped region spanning nearly half the dwarf planet's diameter, bright against the darker terrain surrounding it, as if the distant world had been marked by some ancient gesture of tenderness. This region came to be known as Tomball Regio, named in honor of Clyde Tombaugh, the patient observer whose careful work had first revealed Pluto's existence to the world decades before. The western lobe of this heart, a vast plateau called Sputnik Planitia, revealed itself to be something extraordinary, a vast expanse of nitrogen ice, frozen solid under the crushing cold of space. These were not the rigid, unchanging glaciers of Earth, locked in place for millennia. Rather, they were something stranger and more active. The nitrogen ice on Pluto moves. It flows, though at a pace so gradual that human eyes would never perceive motion. Yet over the course of thousands of years, the ice itself migrates across the surface like a frozen river. shaped by the gentle pull of Pluto's interior heat and the subtle topography of the ancient rock beneath it. Around and within this nitrogen glacier landscape lay valleys and ridges of water ice, hard as steel, in temperatures that dip below 380 degrees Fahrenheit. One might imagine Pluto as a dead, static place, yet the New Horizons images told a different story. The surface bore witness to what planetary scientists call cryovolcanism, the eruption of water and other ices rather than molten rock. There are mountains on Pluto made entirely of water ice, as tall as the Rocky Mountains here on Earth, standing as monuments to internal forces that continue to shape this small world in the deep reaches of our solar system. The bright heart of Pluto raised profound questions among those studying the data. Why was Tombaugh Regio so reflective? Why did nitrogen ice, which should be uniform and featureless, display such remarkable texture and variation? What could have caused Pluto's surface to retain such clear evidence of geological activity, when so many smaller worlds in the solar system have been geologically silent for billions of years? The answers, it turned out, were bound up in Pluto's very nature as a world caught between extremes. Surrounding the bright heart lay darker terrain, sometimes referred to as the chumps or Cthulhu macula by the research team, regions of older, more heavily cratered surface where methane ice and other volatile compounds had accumulated over billions of years. These regions appeared almost reddish in color, likely due to the presence of tholins, complex organic molecules formed when ultraviolet light from the distant sun strikes frozen methane and other simple compounds. Imagine the slow, patient work of radiation reshaping a surface over the course of epochs, gradually darkening it, gradually changing its chemistry, all under the cold, patient gaze of a star so distant it appears as merely another bright point among the stars. Yet perhaps the most intimate revelation came from the detection of Pluto's atmosphere. For decades, astronomers had speculated that Pluto, despite its great distance from the Sun, might retain a tenuous atmosphere of nitrogen and methane vapor. New Horizons instruments confirmed this, measuring the pressure and composition of gases clinging to Pluto's surface. This thin envelope of air, if one could even call it that, exists in a state that defies easy earthbound intuition. Molecules of nitrogen and methane escape from Pluto's frozen surface into space, only to be captured again and refrozen on the cold night side of the dwarf planet. It is an atmosphere that constantly leaks away and constantly reforms, a patient exchange between solid and gas occurring in the profound silence of the outer solar system. The presence of this atmosphere raised another subtle mystery. On the sunlit side of Pluto, temperatures rise slightly higher, relatively speaking, as sunlight warms the nitrogen ice. This modest increase in warmth is enough to cause nitrogen to sublimate from its solid form directly into vapor, a process that requires no intermediate liquid stage. This vapor rises gently from Pluto's surface, flowing across the landscape like invisible water, carrying with it traces of methane and other compounds. As this atmosphere drifts toward the cold night side, where temperatures plummet to even lower extremes, it freezes again, accumulating in frost deposits in shadowed craters and depressions. Pluto, in this way, breathes. It is a slow, barely perceptible respiration, yet it is respiration nonetheless, a rhythm of exhalation and inhalation that continues every Plutonian day, every Plutonian year, a cycle that has perhaps continued for billions of years, utterly alone in the dark. The images from New Horizons revealed surface features that suggested this world is not as geologically dead as distance and cold might suggest. There were canyons and cliffs, evidence of faulting and tectonics, suggestion that Pluto's interior still possesses enough heat to drive geological change. Whether this heat arises from radioactive decay deep within Pluto's rocky core, or from some other source as yet not fully understood, remains an open question, one that scientists continue to ponder in the quiet spaces between observations and data. What New Horizons gave us was not final answers, but rather a new set of questions, each more intriguing than the last, and each inviting further exploration of this strange, distant world. Pluto, small as it is, harbors one of the most tender celestial partnerships in the solar system, and it takes the form of a dance so perfectly balanced that it borders on the improbable. You see, Pluto does not travel through space alone, orbiting the Sun with a single moon trailing behind it as most planets do. Instead, it shares its journey with Charon, a world so massive relative to its primary that the two bodies do not truly orbit one another in the traditional sense. Rather, they waltz around a common center of gravity that floats in the empty space between them, a gravitational midpoint where the pull of each world meets the pull of the other in perfect equipoise. When Charon was discovered in 1978, astronomers initially understood it as simply another moon, a satellite captured or formed near Pluto. But as decades passed and observations accumulated, a quieter truth emerged. Charon is so large, nearly half the diameter of Pluto itself, that calling it a moon felt increasingly like a mischaracterization, a language that no longer fit the reality. The barycenter, that invisible pivot point, actually orbits outside Pluto's surface. If you were standing on Pluto's far side, facing away from the Sun, Charon would wheel overhead in the sky, always hanging in the same position, never rising or setting, never moving. This is the gift and the binding constraint of tidal locking. Both worlds are tidally locked to each other. This means that just as the moon always shows Earth the same face, Pluto and Charon are forever oriented toward one another. The same hemisphere of Pluto gazes perpetually at Charon, and likewise, the same face of Charon stares eternally back. It is a relationship of absolute intimacy and absolute stillness, where change happens on geological timescales, rather than in the turning of days. The surface of Pluto that faces Charon will never see the rolling approach of that great companion world. For billions of years, it has simply always been there, hanging in the same position in the sky. The distance between them is not so great as one might expect. Where the moon orbits Earth at roughly 240,000 miles, Charon orbits at the heart of Pluto's system at just 12,000 miles away. This proximity, combined with their comparable masses, creates a gravitational intimacy that shapes everything about how they exist together. If you could somehow stand on the edge of Pluto facing Charon, that companion world would loom enormous in your sky, covering an arc of perhaps 20 degrees, far larger than the moon appears to us. The shared barycenter they orbit means that Pluto itself, despite being the more famous of the two, actually wobbles in response to Charon's pull. Pluto traces a small, methodical circle around this center point, while Charon traces a larger one, their periods in perfect synchronization. The music of their orbital mechanics is what physicists call a resonance, a harmony in the celestial sense. Their orbital period, the time it takes for both to complete one circuit around their shared pivot, is 6.4 Earth days. Both bodies have rotation periods that match this number precisely. This means that as Pluto spins once, it completes one orbit around the barycenter. As Charon spins once, it too completes one orbit. There is an elegance here, a kind of inevitability, that suggests this configuration has persisted for eons, perhaps stabilized by the very forces that created it long ago. What might have formed this system remains partly speculative, though we may venture a gentle hypothesis. Some astronomers propose that Pluto and Charon were not always dancing in this locked embrace. Instead, perhaps billions of years ago, a collision between Pluto and another Kuiper belt object knocked loose a great fragment. This fragment may have coalesced in orbit, eventually becoming Charon, and the orbital mechanics gradually drew the two worlds into their current state of mutual tidal locking. Others suggest that Pluto captured a passing body, though the mathematics of such a capture at the outer edges of the solar system seem less convincing. The New Horizons spacecraft, as it approached the Pluto system in 2015, revealed the architecture of this binary dance in unprecedented clarity. The images showed us a Charon that is far from featureless. Its surface bears deep canyons, mountains that rise from ice, and shadowed regions that suggest ancient geological activity. One enormous chasm, Serenity Chasma, stretches across much of Charon's face, a scar from some violent event in its distant past. And in the region nearest to Pluto, there is a smoothness, a plainness, that may indicate nitrogen-rich frosts, materials that may have migrated across the space between the worlds, material exchanged through the delicate gravity that binds them. Perhaps the most poignant detail lies in what we cannot see. From any point on Pluto, an observer looking toward Charon would see the same face, never a turning away. And from Charon, the same unchanging view of Pluto would hang in the void. They are bound by what we might almost call devotion, though of course they are merely responding to the laws of physics. Yet those laws have arranged them in a way that speaks to something deeper in us. Two small worlds, locked in eternal mutual regard, orbiting together through the cold and the dark, never leaving one another, never turning their faces away. And if we drift further still, past the orbits of Pluto and Charon, into the Kuiper belt's quieter reaches, we encounter a world so profoundly strange in its geometry that astronomers at first struggled even to believe the data their telescopes were returning. Its name is Haumea, a Hawaiian goddess of fertility and childbirth, though this dwarf planet bears almost nothing of the sphere we might expect from celestial bodies. Instead, Haumea is elongated, stretched. It appears in images like a vast cosmic egg tilted slightly on its axis, wider at its equator than it is tall, a shape so unusual that for years after its discovery in 2004, researchers questioned whether they were seeing it correctly. The cause of this peculiar form lies in Haumea's spin. This dwarf planet rotates extraordinarily fast, so fast that a single day on Haumea lasts only about 4 hours. Imagine a world that completes a full rotation in less time than it takes to watch a film. At this astonishing speed, centrifugal forces pull the dwarf planet's equatorial region outward, stretching it like clay on a potter's wheel spinning at impossible velocity. Matter at the poles is drawn inward. The whole world elongates. What we see now, distant in the darkness, is the result of that relentless spinning, a world shaped not by gravity alone, but by motion itself, by the tireless fling of its own rotation. But there is something else about Haumea that speaks of ancient violence, of a collision so profound that it may have set in motion all that followed. Circling this elongated dwarf planet are rings. Only a few objects in our solar system possess rings. Saturn, with its magnificent system, Jupiter with its faint threads, Uranus with its dusty dark strands, and yet Haumea, small and distant, also cradles rings around itself. 2 main rings have been detected, orbiting the dwarf planet's equatorial plane in the quietness of deep space. How such rings came to be is a matter of careful speculation, and astronomers have woven together a gentle hypothesis, drawn from the clues the dwarf planet offers. The rings may be a relic. Long ago, many billions of years past, when the solar system's architecture was still settling into its current form, Haumea may have experienced a catastrophic impact. Imagine 2 worldlets, perhaps companions orbiting nearby, drawn together by gravity and destiny, colliding at speed across the darkness. Such an impact would not have destroyed Haumea outright. The dwarf planet is hardy, its interior strong, but it would have shattered something nearby. A moon, a smaller satellite that orbited it. The collision would have sent fragments into space, debris spinning outward in all directions. Over time, some of these fragments would have been captured back into orbit around Haumea, eventually settling into the stable paths we observe today as rings. Others may have coalesced into the small moons that Haumea is known to possess, including Hi'iaka and Namaka, each following their own gentle orbits through the darkness. This collision hypothesis is reinforced by something remarkable. The moons of Haumea appear to have been born from the same cataclysm. Their compositions and orbital characteristics hint at a shared origin, as though they were once parts of a larger system that was torn asunder and then reassembled, slowly, into new configurations. What violence looks like when seen across billions of years is transformation. Chaos becomes order, fragments become worlds. And yet, perhaps the collision itself was not the final chapter. Haumea's extreme rotation, that rapid 4-hour spin, may be a separate consequence of impact or encounter. Dwarf planets do not typically rotate this quickly. Such speed suggests that at some point in Haumea's history, another body struck it at an angle, transferring momentum, angular momentum, spinning the world faster and faster until it adopted the shape we see now, a glancing blow from space, a kiss of gravity and matter that rewrote the geometry of an entire world. In the silence of the Kuiper Belt, where Haumea keeps its slow vigil around the distant sun, we see the patient records of its past written into its very form. The elongation, the rings, the rapid spin. Each is a story of collision and survival, of transformation through impact. And yet Haumea orbits on, serene in its strangeness, a reminder that even the most unusual shapes in our solar system have reasons for being as they are. Even the most elliptical paths have their origins in moments of profound disturbance, now settled into quiet rhythms that persist through the ages. And if we turn our gaze further still, beyond the cold kingdoms of Pluto and Haumea, we find ourselves approaching another solitary realm, a world so distant that sunlight reaches it as little more than a faint, distant star in its own sky. This is Makemake, named for the creator deity of the Rapa Nui people, a dwarf planet that dwells in profound isolation some 50 times farther from the sun than Earth, orbiting in a silence that is almost difficult to comprehend. When astronomers first detected Makemake in 2005, it appeared as something of a surprise, a world nearly as large as Pluto itself, yet so remote and so dark that it had eluded detection until relatively recent years. Even now, it remains one of the least understood of the dwarf planets, a place we know through the thin whispers of distant light and mathematical inference, rather than through any close encounter. The few images we possess arrive from telescopes positioned far from Makemake, and so what we understand of its nature comes largely from careful study of how light behaves when it passes through its thin, faint atmosphere and reflects from its frozen surface. The surface of Makemake, as far as our instruments can discern, is blanketed in a thick coating of methane ice, frozen methane, the same compound that rises as a gas in Earth's atmosphere, here locked solid beneath temperatures that hover around 55 degrees Kelvin. This methane frost glimmers faintly under the distant glow of the sun, but the glow itself is so weak, so attenuated by the vast gulf of space, that Makemake exists in a kind of perpetual twilight, neither truly dark nor illuminated in any way that would be recognizable to our eyes. There are also deposits of nitrogen ice upon its surface, perhaps mixed with traces of methane in a slow, frozen chemistry that continues, molecule by molecule, even in the profound cold. What strikes the mind about Makemake is the simplicity of its existence, the absence of noise or commotion, the way it simply continues its long orbital journey, unmarked and unobserved by anything that might notice. There is something almost meditative about the thought of this distant world, slowly processing its way around the sun, once every 309 years, the same amount of time it takes light to make the journey from Makemake to Earth. One might wonder what happens on a world where the sun is so faint that it casts almost no shadow, where temperature and pressure and the fundamental constants of chemistry operate in a realm so foreign to our own experience. And yet Makemake is not truly alone in its distant region. In 2015, astronomers detected a small moon orbiting the dwarf planet, designated MK2, a body so faint and so distant that its presence was inferred more than directly observed, a small companion caught in Makemake's gravitational embrace. This moon is thought to be perhaps 1/7 the diameter of Makemake itself, a diminutive world that traces an orbit around its primary in the darkness, the two bodies dancing together in a rhythm so slow that it might take nearly a quarter of a year for MK2 to complete a single orbit. To imagine this is to sit with a particular kind of loneliness, not the loneliness of isolation, but rather the loneliness of quiet companionship. Makemake and MK2 orbit their common point of gravity, bound to one another by forces that will persist for eons to come, yet separated by vast distances that dwarf even the distance from the Earth to the Moon. MK2 receives no discernible heat from the Sun at Makemake's distance, and the dim primary above it casts almost no light across its surface. What does the smaller moon see when it looks outward? Perhaps it sees, on occasion, the faint pinprick of the sun, distinguishable from the stars only by the slimmest margin, and that is all. The very existence of this moon suggests something intriguing, that even in the deep frozen outposts of the solar system, worlds can collide, can form pairs, can establish relationships that will endure across billions of years. The presence of MK2 hints at a history, perhaps a chaotic history, in which smaller bodies were drawn together, or in which Makemake itself suffered a collision or a near miss that left it with a permanent companion. Yet this history is written in a language we are only beginning to learn, and much remains speculative, much remains shrouded in the darkness that blankets these distant worlds. Makemake continues its slow pilgrimage, and MK2 with it, tracing a path through the void that is so gradual, so gentle, that from the perspective of a human lifetime, they appear almost motionless. Yet they move, and they will continue to move, completing their orbits with a regularity that is almost beyond human comprehension. There is a kind of peace in contemplating this, the peace of understanding that there are worlds beyond our world, realms of cold and darkness and profound quiet, where chemistry proceeds at its own pace, and gravity maintains its ancient relationships, unmindful of the billions of years that pass. And yet, beyond even the orbit of Pluto, in the realm where the sun becomes merely the brightest point among countless stars, there drifts a world that would forever change how we see the solar system itself. Eris orbits in the scattered disk, that ragged outer frontier where the sun's gravitational hand grows so faint that comets take millions of years to complete their journeys around it. It is cold beyond measure, a distance so immense that sunlight, traveling at the fastest speed anything can travel, takes over 14 hours to reach this distant sphere. When you look at the numbers, when you really let them settle into your mind, Eris orbits at an average distance of nearly 15 billion kilometers from the Sun. That is roughly 4 times farther than Neptune. That is so far that the Sun itself, if you were standing on Eris, would appear as nothing more than an unusually bright star in the blackness. For many decades, this world remained unknown. The scattered disk is called scattered for a reason. Its objects do not orbit in a neat, organized plane like the inner planets. They tumble through space along eccentric, angled paths, as if they had been cast there by some ancient catastrophe and never quite settled into orderly motion. And in this chaos, this beautiful disorder, Eris hid in the darkness. It was not until 2005 that astronomers using ground-based telescopes finally resolved its presence. Michael Brown and his team at Caltech were studying the region methodically, patiently, much as Clyde Tombaugh had scanned the skies decades before. What they found was a dwarf planet that rivaled Pluto itself in size, possibly even exceeding it by a narrow margin. This discovery carried implications far beyond the mere identification of a new world. Can you imagine the quiet realization that must have dawned on those astronomers? Here was a body in the outer solar system that was comparable to, or perhaps larger than, the ninth planet that had occupied our imaginations for 76 years. It raised an uncomfortable question, one that would ripple through the astronomical community like a stone dropped into still water. If Eris was a planet, and if Pluto was a planet, then what about the hundreds of other icy bodies in the scattered disk and Kuiper belt that were similar in character, if not identical in size? This discovery of Eris did not cause the reclassification immediately, but it certainly prompted the conversation. It made the question unavoidable. Astronomers could no longer pretend that the solar system contained 8 planets and one anomaly. The discovery forced a reckoning with categories, with the very language we use to organize the cosmos. And in that reckoning, the International Astronomical Union found itself tasked with answering a deceptively simple question: what, fundamentally, is a planet? The meetings that followed were not contentious in the way that headlines sometimes suggested, but rather they were careful, measured deliberations about definitions and taxonomy. And at the heart of those discussions stood Eris, that distant, icy world that had emerged from the darkness to shake the foundations of our solar system's familiar order. Eris itself is a peculiar and fascinating place. Its surface, insofar as we can know it from the vast distance that separates us, appears to be covered with a thick coating of methane ice mixed with nitrogen frost. Much like Pluto, though Eris seems even more reflective, as if it were coated in a layer of fresh snow, perpetually undisturbed by any wind or weathering process. And yet there is something profoundly lonely about Eris, something that speaks to the isolation of the outer reaches of our solar system. It spins slowly, taking over 9 hours to complete one rotation. Its year, the time it takes to complete one orbit around the Sun, is extraordinarily long. Eris takes roughly 567 Earth years to orbit the Sun. 567 years. Think of the sheer patience, the glacial slowness of such an orbit. When Eris was last at its closest point to the Sun, which astronomers call perihelion, the year was 1834. We were in an entirely different world then. The next time Eris will pass through perihelion will be in the year 2257. That is when it will make its closest approach to the Sun in this vast cycle that began long before human civilization emerged and will continue long after we are gone. The orbit of Eris is highly eccentric, meaning it is stretched and elongated rather than circular. At its closest approach to the Sun, it ventures to about 97 billion kilometers. At its farthest, it retreats to about 98 billion kilometers. These numbers, these vast distances, can numb the mind if you contemplate them too long. But there is something meditative about it too, something that speaks to the patient unfolding of cosmic time. Eris dwells in a realm where the gravitational pull of distant stars begins to rival that of the distant Sun. It orbits in near total darkness, bathed only in the faint light of that remote stellar fire far behind it. Occasionally, astronomers observe the faint glow of Eris as it catches and reflects what little sunlight reaches it across the gulfs of space, a pale ghost of reflected starlight that reminds us of its presence. What makes Eris particularly significant, beyond its historical role in prompting the reclassification of Pluto, is what it represents about the outer solar system itself. Eris is not alone in its distant orbit. There are other scattered disk objects that rival it in size, such as Gongong, Makemake, and Haumea, names drawn from the mythology and languages of cultures around the world, a quiet acknowledgement of human imagination reaching toward the cosmos. Together, these distant worlds form a community of icy bodies, ancient remnants from the earliest days of the solar system, when planetary formation was still unfolding according to principles we are only beginning to understand. They dwell in regions so remote, so removed from the warmth and light of the sun, that they might as well orbit another star entirely. And yet they are ours, part of our solar system, part of our cosmic neighborhood, even if that neighborhood extends across billions of kilometers into the cold and the dark. Beyond even the scattered disk, where Eris completes its glacial orbit, there exist objects whose paths seem drawn by an invisible hand, ellipses so extreme and so distant that they pull away from the sun's influence almost entirely, drifting into a realm that feels less like part of our solar system and more like the threshold of interstellar space itself. One of these strange wanderers was discovered in 2003, and astronomers named it Sedna, after the Inuit goddess of the ocean depths, a fitting name for a world that dwells in such profound isolation and cold darkness. What makes Sedna so peculiar is not its size. It is relatively modest, perhaps half the diameter of Pluto, but rather the trajectory it follows through the void. Its orbit takes it as close as 76 astronomical units from the Sun on its nearest approach, a distance that would place it far beyond Neptune's average zone, and then carries it out to an almost incomprehensible 937 astronomical units at its most distant point. An astronomical unit, as you may know, is the average distance from Earth to the Sun, so Sedna spends most of its extraordinary 11,400-year orbit traveling through a realm of such profound cold that the Sun appears not as a warming orb, but merely as the brightest of stars, a pale light amid the greater darkness. The slowness of this journey creates a kind of cosmic patience, a rhythm so extended that human civilization rises and falls many times over before Sedna completes even one full circuit. The unusual geometry of Sedna's path presented a mystery that has occupied astronomers' thoughts for more than 2 decades. When an object orbits the Sun, its orbit is shaped by the Sun's gravity, and the closer an object passes to the Sun, the faster it moves, while the farther reaches of its path stretch long and slow. Yet Sedna's closest approach remains so extraordinarily far from the Sun that one would expect its orbit to be gradually scattered or disrupted by the gravitational influence of the giant planets, pulled into a wider, more eccentric pattern over millions of years. And yet Sedna's current orbit is remarkably stable, confined in a way that suggests something else is at work, something that is shepherding it along its lonely path. This observation has given rise to one of the most tantalizing speculations in modern planetary science: the possibility that another massive body orbits somewhere in these extreme reaches, a world so distant and so dark that it has eluded direct observation. Some researchers have wondered if a 9th planet, a true planet-sized object, unlike the dwarf planets that populate the inner reaches of the distant solar system, might be orbiting in the scattered disk or beyond, exerting a gravitational influence that clusters objects like Sedna into similar orbital configurations. This hypothetical world, sometimes called Planet 9 or Planet X, has never been directly seen, and its existence remains in the realm of careful inference rather than confirmation. The mathematics suggest it could exist. The observations seem to point toward it, and yet the telescopes have not yet found it. Other detached objects, those whose orbits carry them so far from the Sun that they barely experience its gravitational tug at all, have been discovered in recent years, each one following a path that seems subtly influenced by some massive unseen presence. There is Gong Gong, discovered in 2007, whose reddish surface and extreme distance speak to the cold chemistry of the primordial solar system. There is Eris's moon, Dysnomia, orbiting in near darkness. And there are smaller, fainter objects still, each one a small island of rock and ice, floating in a sea of emptiness so vast that the human mind can scarcely comprehend it. When these objects are mapped together, their orbital parameters seem to cluster in ways that random scattering alone cannot easily explain. They appear to be members of a family, shepherded by something, arranged by forces we have not yet fully understood. The question that hangs gently in the background, then, is whether these objects are truly alone out there, or whether they share their isolated realm with a dark, massive companion that has left traces in their gravitational signatures but has so far eluded our sight. If such a body exists, it would be perhaps 10 times the mass of Earth, orbiting in a region so remote that the sun's light would barely warm its frozen surface, and its day-night cycle would span thousands of Earth years. What would such a world be like? Would it have moons of its own, orbiting in that perpetual twilight? Would its surface be blanketed with frozen volatiles, methane and ammonia and nitrogen, in states so cold that they approach their solid forms? The speculation is gentle, careful, always hedged with the acknowledgement that we simply do not yet know. The search continues, using ever more sensitive telescopes and computational methods to predict where such a body might lurk, how its gravitational influence would bend the light of distant background stars, what its thermal signature might reveal to infrared instruments. Some observers scan the skies with patience, sector by sector, aware that they might be looking for something as faint and elusive as a grain of sand against the darkness of space. Others refine their models, running simulations that explore the likelihood of different scenarios, asking whether the orbital patterns we observe could arise from something other than a hidden planet, whether the chaos of the early solar system might have naturally scattered some objects into these extreme paths, or whether encounters with passing stars billions of years ago might have tugged things into their current configurations. Yet the evidence continues to whisper its quiet suggestion, and the mystery remains, like a word on the tip of the tongue, almost clear but not quite graspable. What lies in the outer reaches, beyond the point where the sun's warmth becomes negligible and the cold becomes absolute? Is there something there, waiting to be found, still holding secrets about how our solar system formed and evolved? Or are the detached objects truly orphaned, their peculiar orbits the natural outcome of the chaos and violence of the primordial solar system? These questions hang in the vast quiet, unanswered, but never ceasing to draw the curiosity of those who study the distant reaches. Between the orbit of Neptune and the edge of the sun's gravitational reach lies a realm of profound stillness, a vast, cold collar of icy bodies moving in their patient orbits, nearly untouched since the solar system's first moments of formation. This is the Kuiper Belt, and within it lies something like a frozen library, each object a page in the story of how worlds are born. For centuries, astronomers knew the asteroid belt well enough, that band of rocky fragments spinning between Mars and Jupiter, a graveyard of material that never quite became a planet. We have visited it, mapped sections of it, sent probes to kiss its largest member. The asteroid belt feels almost familiar to us now, a place whose rhythms we have begun to understand. But the Kuiper Belt operates in a different register entirely, at a distance so profound that even our fastest spacecraft take years to reach it. Where the asteroid belt is relatively nearby and densely populated in cosmic terms, the Kuiper belt is sparse, cold, and patient, a freezer that has barely been opened. What makes this distinction so gentle yet so profound is what each region tells us about the moment the solar system was young. The asteroid belt, as we understand it now, is not simply a collection of leftover building blocks. It is the remnant of a much more violent place. In the early solar system, somewhere around 4.5 billion years ago, countless planetesimals, small bodies of rock and ice, orbited in that region between Mars and Jupiter. Many collided and merged. Some were ejected outward by gravitational encounters with the growing giant planets. A few were scattered inward, falling toward the sun. What remains is a thin shell of what once might have been, a shadow of the cosmic construction site that once thrived there. The asteroid belt, in other words, is a fossil of destruction and motion. The Kuiper belt, by contrast, preserves something different. It represents the vast majority of material that formed in the outer solar system and simply remained. Out there, beyond Neptune's distant orbit, the spacing between objects is so great that collisions are extraordinarily rare. Bodies formed, settled into their orbits, and have since moved through the cold darkness in nearly uninterrupted solitude. This makes the Kuiper belt less a graveyard and more an archive, a place where the original conditions of the solar system's formation are frozen, quite literally, in ice and rock. To understand why this distinction matters, one must consider the composition of each region. The asteroid belt is primarily rocky, with some metallic content. It formed close to the warmth of the young sun, where volatile substances like water and methane could not remain solid. The Kuiper belt, by contrast, is made almost entirely of frozen volatiles, water ice, methane ice, ammonia ice, and countless organic compounds locked into rigid solidity by the profound cold of deep space. Each dwarf planet, each larger body in that distant region, is essentially a time capsule. The ice within them preserves not only the physical structure of the early solar system, but also something of its chemical composition. When scientists study the reflected light from these distant worlds, they are reading a record written billions of years ago, unchanged except by the slow accumulation of cosmic dust and the occasional impact from a wandering comet. This comparison between the violent, active, relatively empty asteroid belt and the quiet, preserved, sparsely populated Kuiper belt reveals a quiet truth about how planetary systems evolve. The inner solar system, where the terrestrial planets formed and where we live, was a place of tumult and consolidation. Objects grew by collision. Gravity sculpted the chaos into the ordered arrangement we see today, but the outer solar system followed a different path. Because the sun's gravity weakens with distance, and because the material there is spread across such vast volumes of space, the Kuiper belt never experienced the same intensity of compression and conflict. Instead, it cooled, condensed around its dwarf planets and thousands of smaller objects, and then entered a state of slow, persistent motion. A ballet of distant worlds dancing to gravitational music played across billions of kilometers. What does this tell us about the solar system's birth? Perhaps everything that matters. The asteroid belt shows us what happens when planetary formation becomes crowded and competitive. The Kuiper belt shows us what happens when the material is too distant, too dispersed, too cold to gather itself into a single world. Together, they form a kind of cosmic double helix, one strand of creation and collision, the other of stillness and preservation. The asteroid belt asks, what happens when things come together too quickly? The Kuiper belt whispers back, what happens when they remain forever apart? Scientists have found evidence suggesting that the early solar system was different from what we observe now. The giant planets may have migrated outward or inward, or shuffled their positions in complex dances now lost to time. If this occurred, and most planetary theorists believe something like this must have, then the Kuiper Belt would have been profoundly affected. Perhaps bodies formed closer to the Sun and were later scattered outward by gravitational interactions with the young Jupiter. Perhaps the belt itself was once more densely packed and was subsequently depleted by interactions with passing stars in the solar system's first stellar cluster. We do not yet know the precise history, but what we do know is that the Kuiper Belt, as it exists now, is a stable system. It has been stable for billions of years. This stability itself is a kind of message, a record of an equilibrium reached long ago and maintained without fanfare or drama. One finds, in contemplating these distant frozen worlds, a sense of profound patience. The asteroid belt churns in its confined region, occasionally ejecting an object toward Earth, sometimes gifting us with a meteorite that falls on our continents. It remains active in human consciousness because it affects us. The Kuiper Belt, by contrast, exists in near-perfect silence. Its objects follow their orbits with metronomic precision. Dwarf planets like Pluto and Haumea and Makemake move through the darkness at speeds measurable only in kilometers per second, crossing vast distances in centuries. In this realm, nothing hurries, nothing competes. The universe here operates on scales so vast that 1,000,000 years of human history passes like a single breath. And yet, beneath all this quietude, there is a story waiting to be read, a story written in ice and rock, in the arrangement of worlds across space, in the subtle gravitational choreography that keeps everything in its place. The Kuiper Belt is not a wasteland or a forgotten corner of the solar system. It is a library, and we are only beginning to learn how to read its pages. And so the story shifts now to the journeys themselves, not the arrival, but the vast, patient crossing of cold and darkness that brought our instruments to these distant worlds. There is something profoundly settling about the missions designed to study dwarf planets, something in their tempo and their solitude that speaks to the rhythms of deep space itself. The Dawn spacecraft, launched in the September of 2007, began its long arc outward with a mission unlike any before it. Rather than rushing past a single target and recording what it could in fleeting moments, Dawn was designed with a kind of deliberate slowness built into its very bones. It would visit 2 worlds, lingering at each one in a slow orbital dance. The asteroid Vesta came first, and then, after years of patient coasting through the vast gulf between worlds, Dawn would eventually reach Ceres. But those years of transit, they were not empty. They were filled with the hum of ion engines, with the gentle push of solar wind captured and accelerated by magnetic fields, propelling the spacecraft forward at speeds that seem rapid to us, but are, in the context of interplanetary distance, more of a drift than a flight. Months passed into years. The spacecraft fell silent in its travels, not truly silent, but remote from all human contact, carrying its instruments through a realm where the light from the sun grows steadily dimmer, where Earth becomes not a world, but a point of pale blue, and then merely a memory of light. When Dawn finally arrived at Ceres in 2015, it had been 8 years in transit, 8 years of waiting, of the spacecraft moving through darkness while on Earth. Seasons changed, governments shifted, and human concerns swirled in their brief and urgent cycles. The spacecraft simply continued its gentle fall toward that distant, icy world. And when at last its instruments awakened and began to return images of Ceres's cratered, mysterious surface, there was in that achievement a deep and almost melancholic beauty, the vindication of patience, of sending something fragile and small across such immeasurable distance, and having it arrive, intact and purposeful, at its destination. New Horizons, by contrast, was born from a different kind of urgency. Pluto, that small and distant world that had spent decades at the edge of human imagination, was slipping further away. Its elliptical orbit was carrying it toward Aphelion, the farthest point from the Sun, and the window to reach it, while spacecraft technology remained capable of the journey, was closing. There was pressure in this mission, a sense of now or never, and so New Horizons was launched in 2006 with more velocity than Dawn had ever carried, faster, more direct, a kind of arrow shot across the solar system toward a target few had thought we would ever see up close. And yet, even with this urgency, even with this greater speed, the journey took 9 years. 9 years for the spacecraft to cross the gulf separating Earth from Pluto's domain. In that time, it passed Jupiter, using the great planet's gravity to slingshot itself further and faster into the outer solar system. It drifted past Saturn's realm, past Uranus and Neptune, moving ever outward into a region of space where the Sun is no longer a disk but a star, bright enough to navigate by, but no longer warm, no longer the center of felt experience. The silence of these journeys is difficult for us to comprehend. There is no way to truly convey what it means for a human-made object to travel alone through absolute darkness for so many years, receiving occasional signals from home, but otherwise moving in perfect, unthinking solitude. The spacecraft are not conscious. They do not experience loneliness. And yet there is something in the very fact of their existence that becomes poignant when we consider the vast distances they traverse. They are, in a real sense, the longest journeys humanity has ever undertaken, measured not in the brevity of the experience, but in the sheer emptiness through which they travel. When New Horizons finally reached Pluto in July of 2015, just months after Dawn had settled into orbit around Ceres, the closest approach lasted only a handful of hours. The spacecraft had been traveling for 9 years to spend perhaps 12 hours in Pluto's vicinity, gathering data at speeds that made lingering impossible. And yet in those hours, it sent back images and measurements that transformed Pluto from a distant point of light into a world, a complex, cratered, fascinating world with mountains and valleys, with glaciers and strange dark regions, and that heart-shaped feature that seemed to gaze back at us across the gap of billions of kilometers. The data from that flyby took months to reach Earth, transmitted at the speed of light but across such distance that the signals arrived slowly, patiently, like echoes of a distant cry, gradually becoming audible. The spacecraft itself continued onward, deeper into the outer solar system, its job at Pluto complete, moving toward a series of distant Kuiper Belt objects for flybys that would occur years later, in 2019, adding to the accumulation of knowledge about these strange, remote worlds. What becomes apparent when we follow the paths of these missions is that space exploration, whatever urgency or excitement surrounds it, fundamentally requires a surrender to time. It requires patience of a kind that is almost meditative. The spacecraft must fall through darkness for years, with no guarantee of success, with no certainty that solar panels will continue to function or that instruments will not fail in the cold. They are, in their quiet way, profound acts of faith. Faith in engineering, in mathematics, in our ability to send messages across the void and have them received, understood, acted upon by machines that are, in some sense, our emissaries. And when they arrive, when they finally reach these distant worlds and send back their first images, there is in that moment a kind of exhale, a release of all the tension that has accumulated across the years of waiting. The journey itself, though, remains. Even now, New Horizons continues outward, beyond the orbits of the dwarf planets, toward the heliopause where the solar wind meets the interstellar medium. It carries with it a kind of message, a golden record if we go back further in the Voyager missions, but also simply its existence, proof that we sent something out into the dark, and it reached where we intended it to go. The patience required by these missions mirrors, in some way, the patience required by the objects they study. Dwarf planets are waiting worlds. They have orbited in darkness for billions of years, largely unobserved, rarely visited by anything but small asteroids and the occasional comet. The arrival of human spacecraft is, for them, a kind of disturbance, though they will feel nothing, know nothing of these visiting machines that briefly examine them before moving on or settling into orbit. And yet there is something meditative in the recognition that we have finally, after so long, turned our attention outward far enough to see them, to study them, to treat them not as abstractions or points in mathematical calculations, but as actual places, places with geology, with history, with their own particular beauty and strangeness. Somewhere in the patient mathematics of planetary formation, billions of years ago, these dwarf worlds began their quiet existence, in regions where the sun's warmth had already surrendered to the deep cold of space. The solar system, in its youth, was a far more crowded place than we see it now. A swirling disk of gas and dust and countless small bodies, all slowly colliding, merging, settling into patterns governed by gravity's invisible hand. In the outer reaches, where temperatures dropped so low that water froze solid and methane crystallized into rock, a different kind of world took shape. These were not the rocky terrestrial planets of the inner system, nor the great gas giants that dominate the middle distance. Instead, dwarf planets accumulated from the remnants of that primordial disk, collections of ice and rock, and darker carbonaceous materials, building themselves grain by grain, collision by collision, into the small spheres we now observe with such fascination. What makes their geology so compelling is precisely what sets them apart from their more massive cousins. When a world is massive enough, the heat from its own formation, from the tremendous friction of collisions, from the radioactive decay of elements locked within its core, keeps it warm, keeps it active, keeps it churning. But dwarf planets, being smaller, cool more quickly. They become quiet. They become archives of a colder, more primordial solar system, preserving within their icy surfaces the ancient chemistry of a time before the great planets migrated, before the system settled into anything approaching its current configuration. This is not a limitation of dwarf planets. It is perhaps their greatest gift to us. They are time capsules, and their surfaces tell the stories they have kept frozen for 4.5 billion years. The icy geology of these distant worlds is far more complex than one might initially imagine. Consider ice itself. It is not a simple, inert substance. At the temperatures found on distant dwarf planets, water ice behaves like rock. It is hard, brittle, capable of forming mountains and ridges and vast frozen plains. But this ice is often mixed with other volatile materials: methane ice, nitrogen ice, ammonia ice, compounds that evaporate at different temperatures, that flow and freeze and sublime in response to the subtle changes in solar energy that reach these distant orbits. The crust of Pluto, for instance, contains not merely water ice, but nitrogen glaciers, flowing landscapes of frozen nitrogen, ancient and slow-moving, yet still capable of motion, still capable of carrying heat and material across the surface in ways we are only beginning to understand. What does it say about our universe that ice can flow like glaciers under conditions we once thought only stone could endure? Perhaps the most intriguing possibility hidden within these small worlds is the presence of subsurface oceans. Liquid water, maintained in darkness by internal heat sources. The theory seems almost paradoxical at first. How could a small body, cooling rapidly, sustain liquid oceans in its depths? Yet the physics is sound, and the evidence, though still emerging, is suggestive. Tidal heating. the gentle friction generated as these dwarf planets are pulled and compressed by the gravity of larger neighbors or by their own moon systems, can generate sufficient warmth to keep subsurface water liquid long after a world should have frozen entirely. Ceres, orbiting between Mars and Jupiter, shows gravitational evidence of possible water-rich layers beneath its cratered surface. Could brine oceans, warmer and chemically active, exist even now in the spaces between rock and ice? Some researchers believe so, though the evidence remains tantalizingly incomplete. If such oceans do exist, they would represent something remarkable, not merely geological curiosities, but potential havens for life, should life find its way there through panspermia or through chemistry alone. The existence of liquid water, with minerals dissolved within it, with energy sources from tidal heating, or even, theoretically, from hydrothermal vents on the ocean floor, these are precisely the conditions under which life emerged on Earth. To imagine that such conditions might persist on distant, cold dwarf planets is to expand the possible range of life in our solar system far beyond what we once thought likely. It is speculation, to be sure, but it is speculation rooted in genuine chemical and physical possibility. The icy geology itself suggests something else about these distant worlds. The craters that mark their surfaces, the ridges and scarps and frozen flows, all tell stories of a vigorous past, or at least a more active one than we might have assumed. Pluto's vast Tombaugh Regio, that heart-shaped expanse of nitrogen ice, did not form passively. Its borders show evidence of convection, of warmer material rising at certain boundaries and cooler material sinking elsewhere, a slow churning of ice that mirrors, in its own frozen way, the convection that drives terrestrial plate tectonics. Similarly, the icy mountains of Charon, rising thousands of meters above the surrounding terrain, required mechanisms of uplift and deformation that suggest this moon has not always been geologically inert. Even the most distant, coldest places in our solar system are not utterly still. They move, they change, they preserve memory in their forms. Future exploration of these worlds will, almost certainly, reveal surprises that overturn some of our current assumptions while confirming others we have tentatively held. The proposed missions to the Kuiper Belt speak of spacecraft that would arrive at their destinations decades from now, carrying instruments sensitive to the faint whispers of heat rising from subsurface realms, capable of detecting organic molecules on distant surfaces, equipped to study the thin atmospheres that bloom temporarily when these worlds venture closer to the sun. Imagine the patience such exploration requires. Imagine designing a spacecraft, launching it into the void, knowing that you yourself will not live to see the data it returns. Yet this is the nature of outer solar system exploration. It is an act of faith in the future, a commitment to learning that transcends the individual lifespan. As our understanding grows through both telescope and spacecraft, a broader picture emerges of what dwarf planets truly are. They are not failed planets, though they were once dismissed as such. They are survivors of a different era, worlds shaped by conditions we no longer see operating anywhere in the solar system. They preserve, in their ice and rock, chemical fingerprints of the materials from which the entire solar system coalesced. They remind us that geology, even in the most extreme places, is not a static phenomenon, but an ongoing process, slow and patient though it may be. Their surfaces, mapped only recently in detail, offer lessons in how worlds form, how they evolve, how they maintain themselves across the vast stretches of time that the universe grants to patient observers. And so we arrive at the edge of knowing, at that quiet threshold where the solar system dissolves into the cosmic dark, and perhaps it is here, in this moment of stillness, that we might pause and simply consider the immensity of what surrounds us. These small worlds we have journeyed through, Ceres with her bright sodium carbonate traces, Pluto with his famous heart glowing faintly in the distance, Haumea spinning in her strange elongated dance, Makemake drifting in perpetual twilight, Eris orbiting in the deepest cold. They are not distant abstractions or names on a page. They are real places, solid things suspended in the vacuum, each one rotating on its own hidden rhythm, each one held by the sun's ancient pull, even from beyond the edge of human convenience. And yet from where we sit, from here on Earth, they exist almost as whispers, as suggestions, as reminders that vastness is the true condition of existence. Consider, for a moment, the sheer separation involved. Light from the sun takes 8 minutes to reach us. Light bouncing off Pluto takes 5 hours to travel home. The journey that the New Horizons spacecraft made to reach that distant world required 9 years of flight through silence, 9 years of traveling through the dark at tremendous speed, only to arrive for a brief encounter lasting mere hours before hurtling onward into the outer darkness. And yet in those hours of closest approach, we learned more about Pluto's face, its geography, its atmosphere, than we had learned in all the years since Clyde Tombaugh first noticed its subtle motion on a photographic plate. This is what distance teaches us, that patience and persistence, that the slow accumulation of data over vast stretches of time can illuminate even the most remote corners of our cosmic neighborhood. What does it mean, truly, to contemplate these dwarf planets as resting places, not necessarily as havens or destinations, but as quiet points in space, as places where time moves according to orbital mechanics rather than human urgency, where ancient ice sits in permanent shadow and thin atmospheres escape molecule by molecule into the void, unconcerned with observation or measurement? On these distant worlds there is no rush. On Makemake, the methane frost lies undisturbed by weather, by storms, by the passing of millennia. On the surface of Charon, the great rift valleys remain silent, the product of tidal forces that locked the Moon and Pluto into their eternal embrace millions of years ago. The binary system continues its slow waltz around their mutual point in space, two bodies so close in their orbit that neither quite turns away from the other. And one might wonder whether there is something peaceful in such profound interdependence, such total commitment to a shared trajectory. The Kuiper Belt stretches beyond these named worlds, a vast frozen archive extending further still, populated by countless small objects whose names we do not know and whose surfaces we may never see. They drift in near-perfect silence, disturbed only by the occasional gravitational nudge from a passing neighbor. And Sedna, that strange outlier in her extreme elliptical orbit, moves through even greater isolation, taking thousands of years to complete a single circuit around the sun. We can barely perceive her, can barely imagine her path, and yet she continues, without our witness, without our comprehension, precisely as she must. There is something deeply settling about accepting this, that the universe does not pause for our understanding, that vast portions of reality continue their existence in darkness and cold and silence, utterly indifferent to whether we are watching or not. The dwarf planets are not waiting for our arrival. They are simply being, occupying their spaces in the solar system, existing in their ancient, frozen stillness. And in that recognition, perhaps we might find a kind of permission to rest as well, to allow our own minds to drift without needing to grasp or comprehend or resolve. The solar system, after all, is fundamentally a place of distance and separation. The sun at the center, and then the vast dark between its children, growing colder and emptier as we move outward. Mercury close and scorched, Venus shrouded and hot, Earth in its temperate zone of liquid water and thin air and restless life. And then Mars, and the asteroid belt's quiet tumble, and then the great giants floating in their isolation, and then finally these small worlds at the rim, these dwarf planets that have spent billions of years in the outer reaches, unchanged, unhurried, knowing only the slow rhythm of their orbits and the faint whisper of solar gravity calling them gently around their course. What would it feel like, one might wonder, to exist in such stillness, to live on a world where the sun is merely another star, bright but distant, providing heat enough to maintain the thinnest threads of geology, but not enough to warm the surface above the temperature of deep winter, where all movement is measured in geological time, where change happens at the scale of millions of years, where a day or a year or a human lifetime is utterly invisible against the canvas of your world's history. Perhaps it would be peaceful. Perhaps that kind of timescale, that kind of patient existence, is itself a form of rest that we earthbound creatures can barely conceive of. And so we leave these worlds to their dark and their distance and their slow, eternal dancing around the sun. We have carried the knowledge of them back to Earth, placed their images in our scientific archives, measured their orbits and studied their surfaces, and yet they remain fundamentally themselves, cold, remote, patient, continuing their existence in the vast quiet of space. The New Horizons spacecraft still flies outward, still sends its whispered signals back to Earth across the measured dark, now heading toward something even more distant, even more strange. The Kuiper belt recedes behind it. Pluto fades. The sun becomes a point of light, then fainter still, until even that brief, bright memory of home becomes just one star among billions in a sky that knows neither witness nor intention. And in the stillness of that image, in the profound emptiness and the vast scales and the patient, eternal silence of these distant worlds, perhaps there is invitation enough to let go, to release the weight of knowing, and to drift, as these small worlds drift, through the dark and the cold and the distance, carried by forces we need not fully understand, resting in the certainty that the universe continues its slow work regardless, indifferent and ancient and endlessly patient,